This is Messi from ECEC. Today my seminar topic is probability distribution function, and I am going to explain what is the use of it and what are the properties involved in this. Probability distribution function, capital PDF, also known as cumulative distribution function. It is a function that shows how probabilities are distributed over the possible values of a random variable. So it tells the probability that the random variable takes a value which is less than or equal to a certain number. As we have discussed about the theory of the probability distribution function, let us mathematically see the equation of it. The capital PDF is denoted as capital Fx of x, which is equal to the probability of capital X less than or equal to x. Here in this equation, capital X is the random variable and small x is the real number. And capital Fx of x, it denotes the probability that x is less than or equal to small x. What do we calculate using capital PDF? So we calculate cumulative probability, which is up to a certain value. We can calculate the probability of ranges of the outcomes, like the favorable outcomes which we want to know, and likelihood of occurrence of specific outcomes. Now let us see the expressions for distribution function. There are two expressions for capital PDF. Number one, discrete random variables, and number two, continuous random variables. Discrete random variables. A discrete random variable is a variable that takes specific and countable values such as 0, 1, 2 and so on. So for example, number of heads when tossing 3 coins. Let us assume taking 3 coins, toss each coin one time. Now calculate the probability of heads. So the probability of heads may be 0, 1, 2 or 3. The probability of counting heads is specific and countable. So such examples comes under discrete random variables. And the second example is number of students present in the class. The mathematical form of this distribution function. If the possible values of x are denoted as x1, x2 and so on up to xn, the function is written as capital Fx of x is equal to summation of I is equal to 1 to capital N P of xi into U of x minus xi, where P of xi is the probability of the values in a random variable and U of x minus xi is the unit step function of the given random variables. Now the second expression for the distribution function is continuous random variables. Let us assume if x is a continuous random variable, the distribution function capital Fx of x is the integral of all continuous probabilities of the random variable x up to the values of small x. So let us mathematically give the formula. Let small fx of x be a probability function of the random variable capital X, which is a continuous random variable. Then the distribution function of the random variable x is capital Fx of x is equal to integral minus infinity to x fx of t into dt. Now this is probability density function. Up to now, as we learned about probability distribution function, which is capital PDF, this is probability density function. It is denoted as small PDF. So the probability density function is a mathematical function that helps to describe the probabilistic behavior of a continuous random variable. So it tells us how the probability is distributed over different values of a random variable. The small PDF is denoted as small fx of x. This value gives the density of a particular value at a point of x. Now let us discuss about the relation to capital PDF and small PDF. The small PDF is the derivation of capital PDF, which we denote as fx of x. Now the mathematical equation is small fx of x is equal to d by dx of capital Fx of x. The relation between these two is differentiation. That means if you know the value of capital PDF, you can find the value of small PDF by differentiating it. Let us discuss about the expression for density function. Number 1. Discrete random variables for small PDF. The probability density function small PDF for a discrete random variables is written as small fx of x is equal to summation of I is equal to 1 to capital N p of xi into del of x minus xi. So if we compare this discrete random variables for capital PDF to small PDF, in capital PDF we use unit step function. In density function, discrete random variables, we use del function. So here xi are the probable discrete values of the random variable x. Next, p of xi is the probability of the random variables for each value at a point of x. Here del of x minus xi is the unit impulse function which is centered at the xi. Now the second expression is continuous random variables. A continuous random variable is one variable that can take any value within a given range. For example, if we consider a value within the range of a particular two numbers, it gives the value and it takes the value between the given range. Such variables are used for distribution function. So the probability density function, which is denoted as small fx of x, is the derivation of the capital PDF fx of x. So the mathematical equation is small fx of x is equal to d by dx of capital Fx of x, which is in the range of minus infinity to infinity. This means if you know the value of capital Fx of x, you can find the value of small PDF by differentiating it. Now the properties of probability distribution function capital PDF. Property 1. Fx of minus infinity is equal to 0. So the probability is always a non-negative real number between the values of 0 and 1. An impossible event has the probability 0. So for example, fx of minus infinity is equal to p of x is less than or equal to minus infinity, which is equal to 0. Next, the property 2. Fx of infinity is equal to 1, where the value fx of infinity represents the probability like the random variable capital X takes any value which is less than or equal to infinity. This includes all possible values of the random variable in a sample space. Since the total probability of any random variable across the entire sample space must be 1. So at last we conclude that capital Fx of infinity is equal to probability of x less than or equal to infinity is equal to 1. So in this expression may also written as Fx of infinity is equal to summation of x is equal to minus infinity to infinity p of x is equal to 1 for discrete random variables, or integral minus infinity to infinity fx of x dx is equal to 1 for continuous random variables. Property 3. 0 less than or equal to capital Fx of x less than or equal to 1. This expression states that any probability of the random variable, it lies between the values of 0 and 1. Since Fx of x is a probability value, it must be in the range of probability value. So the value of distribution function can never be negative and it can never be exceed the number 1. Property 4. Fx of x1 is less than or equal to fx of x2 for x1 is less than x2. This function fx of x is non-decreasing. That means it either stays constant or increases at a value of high range. This is because fx of x1 represents the probability that the random variable is less than or equal to small x1, and fx of x2 represents the probability that the random variable is less than or equal to x2. So the probability cannot be decreased as x increases. Property 6. Fx of x plus is equal to fx of x. The probability distribution function is right continuous. This means as we approach a point x from the right, the value of fx of x remains unchanged. So mathematically this can be written as limit x tends to 0 plus fx of x plus e is equal to fx of x. Properties of probability density function small pdf. Number 1. Non-negativity. Fx of x is greater than or equal to 0 for all the values of x. Number 2. Total area is equal to 1. Integral minus infinity to infinity fx of x into dx is equal to 1 for any value and within any range. Number 3. For a continuous random variable capital X, the PDF probability distribution function fx of x is defined as fx of x is equal to integral minus infinity to x fx of t into dt. As we read this formula in the relation between the probability distribution function and probability density function. Number 4. For any two values x1 less than x2, the probability that the random variable capital X lies in the interval between x1 and x2, which is given as p of x1 less than capital X less than or equal to x2 is equal to integral x1 to x2 fx of x into dx. So this is the detailed explanation of the probability distribution function and probability density function. Thank you.